All right, everybody, welcome back to another video on power series. So in the previous video, we learned about what power series were, and we also talked about how to find what are known as their intervals or radii of convergence, because you can't just plug any x value you want into a power series. Sometimes some x values will make the series diverge. So we learned about how to find out what a series IOC is, and we did that typically by doing the ratio test. Also, you can often use the root test as well. That also tends to work well for finding the IOC. So what we're going to do today is we're going to talk about representing certain functions as power series. There are many functions out there that aren't polynomials, but they can be represented as power series, which is sort of the next best thing, an infinitely long polynomial. So what we're going to do is we're going to learn how exactly to represent certain functions as power series. So last time we got acquainted with the power series, the sum from 0 to infinity of x to the nth power. And remember, this was the geometric series. So if we know that our absolute value of x is less than 1, and this is its interval of convergence, then we remember the geometric series formula. This series will sum up to 1 over 1 minus x, so long as whatever our x is has absolute value less than 1, and not including 1. Now, what we can do here is now that we have a representation for one power series, we know 1 over 1 minus x is going to equal 1 plus x squared, and on, if that x is small, then what we could do is we could use this as a base to find the series representations for other functions as well. So the way I like to imagine this, it can be a little bit confusing at first, but the best way to think about this is to imagine this x not as a variable, but as sort of like a blank space. So if we have the sum of something raised to the nth power, so long as that something has absolute value less than 1, then our result will be 1 over 1 minus whatever that thing is. It doesn't need to be just x, it can be anything we want. Now, what our goal for the next few problems is going to be is to turn whatever we start with into 1 over 1 minus something. Because once we get it to that point, we've won, and then we could write it as a series. So say, for example, instead of the function 1 over 1 minus x, maybe I would want the function 1 over 1 plus x. Now, in order for this technique to work, these both need to be exactly 1. They can't be any different number. They need to be 1 for it to be this series. And this also needs to be a minus sign here. But the problem with this is that we have a plus sign. We don't have a minus sign. Well, what is a plus sign but just two negatives multiplied together? We can have this as 1 over 1 minus, and then negative x. And now we have it exactly in the right form. We have this minus right here, and then what's in our blank space? Our blank space is going to be negative x. That means our series representation for this function is the sum from 0 to infinity of negative x to the nth power. Now, for something we're going to do in a few minutes, I want to just get this to be x to a power with nothing inside the exponent n here. So in order to do that, I have this negative to the n. The way that's going to be written is the sum is 0 to infinity. Negative to the n is the same as negative 1 to the n. And then we have x to the n right there. Now you might ask, okay, what's the interval of convergence? Well, that's also easy to find. We can just recycle the interval of convergence we got from the geometric series. So we include negative x right there, and it has to be less than 1. But of course, absolute values don't care at all about negative signs in there. So it turns out that our interval of convergence is going to be exactly the same as it was before. We can plug exactly the same numbers into this that we could that one right there. All right, so that was our first example, and we could do a lot more with this. Like, for example, if I wanted 1 over 1 plus x squared, I could have a negative x squared, for example. And there's a lot of different things you can do here. But the main idea is to write whatever you have as 1 over 1 minus something, and then once you have that, you have your power series. That's the first way we're going to find new power series from old. The second thing we're going to do is actually one of the primary benefits of using series. So these series, they're essentially infinitely long polynomials, right? Now, what's the nice thing about polynomials? Well, in calculus, polynomials are some of the easiest functions to find the derivative and integral of. So let's say we had our series that we just figured out, 1 over 1 plus x, which is the sum from n equals 0 to infinity of negative 1 to the n, x to the n, of course, so long as absolute value of x is less than 1. So what we're going to do and what we're able to do to find new series is that we are going to integrate and differentiate the series that we already have. So what I'm going to do is I'm going to slap an integral sign on both sides of this since it's the same function on either side. So I have the integral of this sum right here. Okay. And then, well, let's see here. So this is an integral, maybe we learned in Calculus 1. The integral of 1 over 1 plus x will be ln of absolute value of 1 plus x. And then maybe we'll get a plus c for that because we did an integral. Now, on the other side, what we're going to do here is we're going to exchange this integral sign in the sum. And there are kind of some technicalities hiding there, but for all the integrals we're going to do of series, this is going to work out just fine. So we have the sum from 0 to infinity of the integral of negative 1 to the n, x to the n dx. Now, notice that this is an integral with respect to x. So anything that doesn't have an x in it is treated as a constant. Namely, this negative 1 to the n is just a constant. So I'm going to ignore that. I could effectively move it out of my integral. And then for x to the n, how do I integrate that? That's just the power rule. So I raise the power by 1 and divide by the new power. So we get that ln of absolute value of 1 plus x, and then plus some constant, is going to be the sum from n equals 0 to infinity. We still have our negative 1 to the n there. But now our x is going to be raised to the n plus 1 power. Whatever that power is, we end up dividing by. So we divide by n plus 1. And voila, we have a series for a natural log of 1 plus x. Well, rather, we almost do, but we need to figure out what this plus c is since we just did an integral. So what you can do is you can plug in a convenient number. Now, in this case, that convenient number is going to be 0. Typically, when we have this x, it'll have plus or minus some number inside there. You usually want to match up what you plug in with that number, which is called the center of the series. Since we don't have any number like that, our center is considered to be 0. So if I plug in x equals 0 to both sides of this, I have ln of 1 plus c is the sum from n equals 0 to infinity, negative 1 to the n, 0 to the n plus 1 over n plus 1. And of course, I don't really care what happens as n goes to infinity here because this will just be 0. But the thing is, we also know that log of 1 is 0 as well. So really, we just have c on this side, and we have 0 over there. So technically, our plus c is going to be 0 in this case. We don't need to have a constant term. So in summary, we see that the series for natural log of 1 plus x, should have some values there, will be the sum from 0 to infinity, negative 1 to the n, x to the n plus 1, divided by n plus 1. All right. By the way, as kind of a note here, sometimes you may see this series written differently. So there are a lot of tables that have common series like this. You might see this one be written a little differently. What some people like to do is they like to turn all of these n plus 1s to n's. So they lower all of these by 1, including the n and the negative 1 there. And you can do that so long as you raise your starting index by the same amount. So what you'll often see this series written as the sum from 1 to infinity, negative 1 to the n minus 1, x to the n, divided by n. And it may look a bit different, but it's actually exactly the same series. This is called reindexing. So typically, you'll see one of these two forms for our series. Now, the thing is, last time when we did a substitution to get 1 over 1 plus x, we were able to use the interval of convergence for the geometric series to get our interval of convergence for the new series. Now for this one, when we integrate, the way it works is that when we integrate, we have the same interior for our IOC. So for example, we noticed that 1 over 1 plus x, that worked from -1 to 1. So these endpoints will be exactly the same, except when we integrate, but we may add endpoints. So when we integrate, if we didn't include the endpoints before, we have the potential to include them after we integrate. And by the way, when we integrate, we'll never lose endpoints. So if we already had both of these, then it would definitely still include them afterwards. But we might gain them if we didn't have them already. So what we need to do is we need to plug -1 and 1 into our new series and then check to see if it converges or diverges, just like last time. All right, so let's do that. Let's try to plug in, let's plug in -1. Okay, I'm going to use this original series I got. So this is the sum from 0 to infinity, -1 to the n, and then I have -1 the n plus 1 divided by n plus 1. All right, now we have the same number raised to 2 different powers, so how do we deal with that? Well, we add the powers together. So this is really the same as -1 to the 2n plus 1. But the thing is that -1 to the 2n plus 1, that's -1 to some odd number. And -1 raised to any odd power, like 1, 3, 5, all of those will just be -1. This is a very fancy way of just writing -1. We have negative, which we can move out of the series, sum from 0 to infinity of 1 over n plus 1. But unfortunately, this is just the harmonic series with a negative in front, so that's going to diverge. So it turns out that we don't include the -1. However, if we try out x equals 1 instead, then we have the sum from 0 to infinity of -1 to the n divided by n plus 1. And this time, my second term was just 1 to the n plus 1, so that just goes away. Now this guy, on the other hand, this converges by the alternating series test, because we have an alternating series and then we have a sequence which is monotonic and going to 0. So it turns out that we can actually include the +1 as our endpoint. So this is going to be our new interval of convergence. And by the way, since these numbers are always going to be the same, the width of the interval will be the same. So whenever we do integrals, and as we'll see in a second, derivatives, our radius of convergence never changes at all. So our radius of convergence for this is still going to be 1, just like it was. Also, another way we could have seen that -1 wouldn't work is that if we plugged it into the function it's representing, we have natural log of 1 minus 1 or natural log of 0, that quantity is undefined. So we definitely know for sure we can't plug in -1. So if you ever see anything like that, you can sometimes skip a series test and just be like, oh, it's not going to represent the function because the function doesn't exist at that point. Also, I can get rid of these absolute values now because any value I can plug into here will make this 1 plus x be positive. So I can just have parentheses there. All right, so that's how we can use integration to get new series. So if you ever see something that looks like the integral of a function whom you know the series for, you just integrate that and then get a new series for the function that you want. All right, so that was integrating. And as I'm sure you can imagine, if we can integrate series, then we could also differentiate them and get new series as well. Let's start with that 1 over 1 plus x series that we had before. This is the sum from 0 to infinity, -1 to the n, x to the n, and its interval of convergence was -1 to 1. Now, my goal for the next part, so let's say I have a function that I want to find the power series for. And that function will be 2 over 1 plus x squared. Okay, so let's see how we would find a series for this. Now you may be tempted to just square everything here and then just put this squared in there. But remember, these power series are like polynomials. So just like you can't put the square on each member of a sum of a polynomial, You can't do that for these series either. So we can't just square these together. We could do some kind of infinitely long foiling thing, but that's probably more difficult than doing it the way we're going to do it. So what I'm going to do is I'm going to take the derivative of this, because I know if I do the derivative of this, this guy down here, the denominator, is going to be raised to 1 power higher by the power rule. So in order to get this, what I'm going to do is I'm just going to take the derivative of both sides of this. This is my goal. Let me write my goal over here. It's not in the way. I want 2 over 1 plus x squared. All right, now what I'm going to do is I'm going to do the derivative. So here's the derivative. I'm going to do the derivative of this as well, d by dx. All right, so I'm going to do the derivative. So I'm going to use the power rule. I effectively have this 1 plus x to the negative 1, so I'll lower that to be negative 2, or 1 plus x squared on the bottom. But then I need to multiply by my old power. My old power was negative 1. So I now have negative 1 over 1 plus x squared. And meanwhile, over here, what we're going to do is we're going to do the derivative of this. Now, just like the integral, there's kind of a technicality when if we can switch the series with a derivative or not, but we're just going to gloss over that here. It's going to work through everything that we're going to do. And also, just like integrals, this guy right here, negative 1 to the n, that has nothing to do with x whatsoever. So we're just going to do the power rule on this x to the n right there. So I keep my negative 1 to the n, and then I do the power rule there. So I have nx to the n minus 1. I bring the current power down, and then I lower it by 1. All right, so there we go. But the thing is, we're not quite there yet. This is the series for negative 1 over 1 plus x squared, but I want positive 2 over 1 plus x squared. Well, the nice thing is that if we're off by just a constant multiple, or actually even a non-constant multiple, what we could do is we could just multiply both sides by what we're missing. So if I multiply both sides by negative 2, that would get me what I want. So I'm going to do that. So if I multiply by negative 2, I get exactly what my goal is. And then meanwhile, over here, I'm just going to have a negative 2 in front of my series. And it's okay to have some kind of coefficient in front of your series. So there we go. We were able to find a series for our goal by differentiating. One final note is that sometimes when you see people write series like this, notice that if we plugged in the 0th term, n equals 0 into here, we would have 0 times the rest of this would be 0. So since that term is not going to do anything anyways, some people just omit that term and then start this at 1. And in the same way, if we took another derivative, brought that n minus 1 down, if we plugged in the 1, that'd be 0 as well. So many people would start that as 2. Honestly, it doesn't really matter whether you have this be 0 or 1. It's still going to be the same series regardless, because the term you're talking about is 0. But I'm just saying that sometimes people might write it this way. So don't be afraid if you see something like that. All right, now one last thing we have to do is we need to know the interval of convergence, because we always need to know what x's are okay to plug into this series. Now, just like integrals, derivatives, if we do the derivative, we have the same interior for our IOC. So since we were negative 1 to 1 before, we're at least going to be negative 1 to 1 now. But unlike integrals, where we could potentially add endpoints, with derivatives, we might actually lose endpoints the more we do derivatives. So for example, if this were negative 1 to 1 inclusive, I would need to recheck those endpoints again to make sure they're still there after the derivative. But the fact of the matter is we didn't even include these endpoints before, so there's no way that they're going to include them after, because derivatives never add endpoints. They can only take them away at most. So we know automatically that our interval of convergence will be the same. And then just like before, our radius of convergence never changes if we do a derivative or integral. So our radius of convergence will still be 1 for this series. All right, so to summarize, we talked about 3 ways of finding series representations for different functions. We talked about integrating, differentiating, and substitution. All right, well, as always, let me know if you have any questions, and I'll see you in the next video.